Welcome to Empowered Learning. This video will be about how to evaluate improper integrals. Specifically, what we're going to talk about is how to define and recognize improper integrals, recognize what type of improper integral you have, and be able to correctly evaluate an improper integral. So before we begin talking about what improper integrals are, we first need to review what a proper integral actually is. And so from understanding what a proper integral is, we can also figure out what things make improper integrals improper. So let's take a look at that first. So let's first look at what a regular definite integral looks like so that we can identify the things that make this type of integral proper. So we were considering a definite integral here. We would normally have something that looks like this, and of course, because of the net change theorem, we would call the antiderivative of little f of x big F of x, and we would normally evaluate that over an interval from x equals a to b. Okay? Now, what makes this integral proper is a few things. One, we know that our function f of x that we are trying to integrate is going to be continuous, and it's going to be continuous on the interval of x values, this closed interval from x equals a to x equals b. So that means that my function is continuous at all x values in between a and b, as well as at x equals a and x equals b. The other thing is that we know that a is going to be greater than or equal to b, and that both a and b are real numbers. Okay? So these are the three main things that make this particular definite integral that I've written here in general a proper integral. So what this also tells us is that if we violate any one of these three things here, and the ones that we're actually going to concentrate on here is going to be, if I name this number 1, number 2, and number 3. The two main ones that we're going to focus on here is going to be number 1 and number 3. Okay. For number 2, we really don't worry about this one because we already have integration property that you've probably learned in first year calculus that will allow you to flip the limits of integration for a definite integral like this and just multiply by -1 to fix that. But for these other two, can't be fixed that easily to make it proper again. Okay. So here, if our function is not continuous on this closed interval for any reason, or if our lower limit or upper limit is not a real number for any reason, then by definition, our integral here that we're looking at, and in this case, this definite integral, will end up being improper. Okay. So what we are going to see is cases where we have integrals to where the function is not continuous, and that could be because it's at the endpoint of a domain, or it could be because the function has a vertical asymptote or some kind of jump discontinuity somewhere in between x equals a and x equals b. Okay. At the endpoint of the domain type situation, we would have the situation where let's say there is a discontinuity at x equals a or at x equals b. Okay. Or we're dealing with a function in and of itself that truly has an end of domain at, let's say, some x equals a or x equals b. Okay. Now, in the case of our a or b not being a real number, the main thing that we're going to see is either a is going to end up approaching a negative infinity, or we're going to have b approaching a positive infinity. Okay. So in those instances where we see one of these limits of integration here actually end up being positive or negative infinity, we know that by definition that's going to be an improper integral as well. Okay. So as I go through all the types and scenarios here in just a second, just keep in mind that the two main things that we're looking at is there some reason why our function is not continuous on this closed interval of x values, and or do we see a situation where one of our limits of integration is not going to be a real number? Okay. All right, so now that we're back to where we want to begin and talking about improper integrals here, just note again that we're going to be looking at definite integrals of this type, to where essentially our function is not going to be continuous at some x value on that closed interval, or our actual limit, one of our actual limits of integration itself, or at least one, I should say, is not going to be a real number. So we see that having infinite limits of integration here is going to be one of the things that will make our proper integral turn improper, as I've mentioned before. And what this also alludes to is the fact that we're actually doing integration over a half open interval. So in the case where our lower limit goes to negative infinity, then what we're saying here is essentially that we're integrating on some half open interval like this, okay, which I've written here. And of course, if the upper limit goes to positive infinity, kind of the same thing. We are integrating on a half open interval. Okay. Now, we see here that I also have the range of some function f of x within limits of integration are infinite. Okay. So that means we have an instance where essentially we're going to have a vertical asymptote, or that the end behavior of the function is such that it just keeps on climbing and getting higher and higher, or lower and lower and lower for the range of x values that I'm doing I'm trying to evaluate the integral. And so it usually means one of those two things. Either you have a vertical asymptote, or you have a situation where, let's say your end behavior, or if you have a piecewise function, that portion of the piecewise function just keeps on going to infinity or negative infinity. Okay. So examples. So we see here that this particular function that we're trying to integrate here, which is 1 divided by x minus 2, it has a vertical asymptote here at x equals 2. And of course, 2 is in between 0 and 4. So this function is going to be, is not going to be continuous for all values of x in between x equals 0 and x equals 4. Okay. So by definition, this is an improper integral because of that. Of course, here as well, if we're taking the definite integral of 1 over square root of x minus 3, evaluated from 2 to 4, then we see that, of course, we have a vertical asymptote at x equals 3. That's in between 2 and 4. So, of course, the function is not going to be continuous for all those x values. So, by definition, these are these are going to be improper integrals. Okay. Now, we're going to see other cases as well as I kind of go through the different types, but that's just sort of the introduction. So in short, we know integrals with at least one of the aforementioned attributes are called improper integrals. Of course, I've already kind of gone over that in a little bit more detail. The main thing to remember here is that improper integrals are classified as being either convergent or divergent, depending upon how you want to say the word. Okay. So in short, an integral that is convergent, you will be able to evaluate the integral, and you will actually be able to get a real number for that answer if you're talking about a definite one. Okay. If the integral is divergent, then what that means is that you're not going to be able to evaluate the integral, and you're probably going to get something like positive or negative infinity, or does not exist for the answer if you try to evaluate. Now, conceptually, all that means is this. We have certain functions that if we try to evaluate it under an improper integral type of situation, some of them will still converge, meaning that even though for whatever reasons that the integral itself is improper, we're still going to be able to have an idea of what the actual area under the curve would be if that's what we're trying to, do the integral for. Okay. When it's divergent or divergent, then in that sense, there's properties going on with the function to where it's not going to be, you're not going to be able to actually calculate what that area is. Okay. And so properties like the function as it decreases too slow for you to be able to actually, figure that out. Okay. And we're going to see a special case type of integral where things like that actually happen. All right, so now we'll discuss the proper definition of an improper integral by looking at the definition of it in two parts, type 1 and type 2. So just to be clear here, what I did here was give you the general overall understanding of what it is that we look at whenever we have a proper integral, and the things that we kind of tune into that are violated with this proper integral definition in order to make it improper. So what we're going to do now is formalize these definitions of what an improper integral actually looks like, and we're going to single out these two cases here. Okay, and we're going to single them out as a mixture of type 1 and type 2 type of improper integrals. So a type 1 improper integral, these are the simplest type, and they deal with a curve that is non-negative, or a function that's non-negative. So we're only considering functions of this type that lie above or on the x-axis. Okay, a type 2 type integral, we're going to deal with. It doesn't matter whether the function lies above or below the x-axis. Okay, now we're going to see that with type 1 integrals and type 2 improper integrals, that there are going to be some other variations of the theme. But from an overall perspective, the type 1 integrals, the improper integrals, have this basic understanding that the function that we're dealing with is always non-negative, whereas the type 2 integrals kind of help us deal with functions that end up having to be lie below the x-axis sometimes. Okay? Now we're also going to look at this integral here, and this is going to be a special type of improper integral that's really going to serve as sort of like a boundary to be able to tell us when certain types of improper integrals are actually convergent versus when they're divergent. Okay. We'll also see in later videos that we're going to have some other theorems that's going to help us out whenever we may not necessarily be able to evaluate what an improper integral is, meaning that it may converge, but we may not have the by hand techniques to be able to do it. But we still have tests to let us know, even though we can't calculate this by hand, we still should be able to find out what an improper definite integral value actually should be. Okay. All right, so let me kind of move on here. I'm going to skip the rest of this, just kind of get to the definitions here. All right, so for our type 1 type of integral, the definition of it is broken down into 3 different, scenarios. So we first see that if we have some improper integral where this value t here, of course, is number 1 going to be greater than or equal to the lower limit, which is fine. But it also can be any value of t that approaches infinity. Okay, so these little markings I've put here are there just to say that this value of t could be anything from a number on up to infinity. So when we write this t here, it doesn't mean just a specific constant value t. What it means is any value that's greater than a on up to infinity. So it's kind of like a catch-all type of notation here. And so going to infinity here for t is just one of the many things that we can put here in place of t in order to satisfy this definition here. So with that in mind, if we have the definite integral of some function f of x from x equals a to another parameter t, which could approach infinity, and we see that that ends up being some finite number, then we know that we can also assume here that the integral of this function as x goes from a to infinity can be rewritten this way. And of course, now you see why we have that quote unquote constant value t there to kind of make it look like it's proper. And what we're going to do is study the behavior of what this definite integral would be as this value of t approaches infinity. And again, if that equals to some real number, then of course we say that the limit exists and thus the integral is convergent. Okay. Otherwise, this particular improper integral will be divergent. Okay, so I'll kind of condense that down. So we're able to evaluate this improper integral where your upper limit here can approach infinity. Then the way that we properly rewrite this is to say, hey, if I have, I'm taking the definite integral of this function from some value to infinity, then I can rewrite it here with my limit operator, and we're going to evaluate this definite integral as if it was proper, and then apply the limit operator to that result to see what we get. And if we get a real number, then we know that this improper integral converges. Otherwise, we see that it's divergent. So for part B of this definition, it's pretty much the same thing, but now we're looking at the t being on the lower limit of integration instead of the upper limit. Okay, and it's the same thing. Whenever we see we have this situation here, we know that we need to rewrite that as limit as t approaches negative infinity of what this definite integral would look like, acting as if it was proper. We evaluate it. If we get a real number for an answer, then the limit exists, which means that the improper integral also converges. Otherwise, it's going to be divergent, which means we're not going to be able to find, and I guess if we use one translation of it, we're not going to be able to find the area under the curve of that particular function. All right, so part C just deals with the fact that sometimes we may want to know the area under the curve from negative infinity to positive infinity. Okay, and so one example of that would be, for those of you that are familiar with statistics, a probability density function. So, of course, probability density function, most people know it as a bell curve. But in looking at that, what you are essentially doing here for the probability density function, I'm going to draw this up like this. What you're essentially doing for this probability density function here is you're trying to find the area under the curve from negative infinity to positive infinity. And of course, how much of the area that you find under the curve sort of relates to a probability, for those of you that are familiar with statistics. Well, this probability density function, when you try to figure out what's going on with it, essentially you are, again, just trying to find the area under the curve from negative infinity to positive infinity. So what we are trying to show you here is that if we are trying to find the area on the curve of something like what I just described, then we could pick a value c that's going to be advantageous for us to kind of break up this integral in, so that it's easy for us to actually evaluate the integral of both pieces of this. So that's pretty much what all this says. Now, the other thing to recognize is that we've broken up this integral into two integrals, but each piece in and of itself is an improper integral that we would have to deal with. And of course, if both of these are improper integrals, then that means that both of them would actually have to be able to end up equaling a real number if we want this particular integral to converge. Let's say if this one actually ended up equaling a real number, but this one did not, then of course this integral here would diverge as a result of that. So either both have to equal a real number and thus they converge, or it will all diverge if at least one of these two actually don't end up equaling a real number. All right, so some other things to know about the type 1 definition. Again, I'm reiterating here that for these types of integrals, we know that our function is assumed to be non-negative. The other important thing to know is that in these instances, a lot of times, what we are trying to do is figure out end behavior of a function, and that's a pre-cal term. And so a lot of times, well, we know that in general, end behavior has three outcomes. And let's say if x is approaching infinity, a function on your graph will either go up to positive infinity, go down to negative infinity, or ride along some smooth horizontal line. And in the case of it riding along a smooth horizontal line, we know by definition that's called a horizontal asymptote. Okay, so this is why I put the second bullet point here that our function may have a horizontal asymptote as x approaches infinity or negative infinity. Okay, and so our type 1 integrals, improper integrals, normally deal with functions that lie strictly above the x-axis, and it has a situation where you're going to be dealing with a horizontal asymptote. Okay. All right, so for the type 2 improper integrals, these are the ones that essentially deal with discontinuities. So I'm going to say discontinuities within the closed interval from A to B. Okay, so for this type, of course, our function could lie above the x-axis or below, or a combination of the two in the interval of x values that we're considering to integrate. We also know that for the type 2 integral, we're going to have vertical asymptotes. Our functions may have vertical asymptotes in them, or they may have some other type of jump discontinuity. Okay. And so the type 2 integrals are mainly defined for that purpose of saying, hey, well, how do you deal with a function that has vertical asymptote or jump discontinuity or some other type of discontinuity within your interval of x values that you're dealing with? Okay, so we see here that if our function is continuous on this half open integral and it has a discontinuity at the upper limit here, then we know that this definite integral is actually improper, and how we're going to deal with it is by studying the behavior, aka take the limit of this definite integral as this upper limit t here is going to approach a value of b coming from the left. Okay, so what that looks like here, let's say I got a function and it's got a vertical asymptote here. Let's say this is x equals b. Then of course what we're trying to do is figure out what's going to be the area under the curve of the function as x approaches b from the left. Okay, and of course this is the left side of the vertical asymptote, that's the right hand side. And so if we're able to evaluate the definite integral and we get a real number answer, then we know that the improper integral converges. Otherwise, it's going to be divergent. So part B, kind of the same thing, but now we're looking at the lower limit now, and we would be approaching A from the right. Okay, so kind of the same scenario here. as we had earlier, but just kind of flip the scenario. And for part C of this definition, let's consider that in between x equals a and x equals b, we have a value c, and that value c has a discontinuity. Okay, so another way of putting that is that our function is continuous on this interval of x values, but you see that that x value c there is in between a and b, but it's essentially not continuous at x equals c. Okay, so what this calls for us to do is to actually break up our improper integral here at the discontinuity and evaluate the improper integral of each term to see if they both are going to converge or not. If they both do, then the improper integral exists, and of course the value converges. Otherwise, it is divergent. All right, so now that we've kind of gone over the basic definitions and you have an idea of the types of integrals that you're going to see, or the types of functions and or x value interval mix that you will see whenever you have an improper integral. Now let's talk about this special case integral, the integral from 1 to infinity of 1 over x raised to the p dx, where p is a constant. So what you're going to see here, that this function 1 over x raised to the p, where p is a constant, is very important, because it's going to act as sort of a litmus test or boundary type of integral to let us know from many definite integrals that we're going to evaluate whether it's going to be improper or not. Okay, well, sorry, whether it's going to converge or not for the improper integral. Okay. Now the note that I have here is just again stating that this is a special case type of improper integral. Now this whole notation of this being infinity here does not mean what it did in the actual definition of an improper integral, where, you know, when I had something that was like this from 1 to t, this meant that I can do anything from, let's say, I can let t be 2, 3, 4, 5, 7.8, square root of 19, all the way to infinity, and that was a catch-all for that. So for this special case, this upper limit here has to be infinity in order for it to work. Okay. Now this lower limit could be any other constant. It could be, you know, 2, 3, 4, 5, 6, 7, whatever. But the upper limit has to be infinity for the result that we're talking about here to work. Okay. And let me get rid of this right quick. All right. So in short, we know that whenever this value of p here is greater than 1, we know that this improper integral will converge, meaning that if we can evaluate what that improper integral's answer is going to be by hand, then we should be able to get a real number for an answer. In the instance to where we are dealing with evaluating an improper integral where the integrand does not have an elementary function antiderivative, we may not be able to figure out what the actual answer is by hand, but we will know that it should end up equaling a real number. And so normally in those situations, we would use numerical integration to be able to do it. So something like the trapezoid rule or Simpson's rule to be able to figure those things out. Okay. Now, if our value of p here is less than or equal to 1, then we know that this integral is going to diverge. Okay. And so essentially, again, what that means whenever it diverges is we're saying that, hey, the answer that we're trying to get to, we're not going to be able to get to. And in this case, the reason why is because, let me fix that right quick, And the reason why is because the function of 1 over x raised to the p, when p is less than or equal to 1, and of course when it's equal to 1, it'll be 1 over x. The way in which this function decreases as x goes to infinity here, and we're trying to find the area under the curve of this, it decreases too slow for us to be able to actually figure out what the area under the curve of this particular function would be from, let's say, x equals 1 all the way to infinity. Okay. Now, if I had something like 1 over x squared, then that's going to look a little different. And just to kind of draw this, 1 over x squared would probably decrease like this, and the area under the curve of this function can actually converge to some real number because of the fact that 1 over x squared decreases to 0 faster than 1 over x does. Okay, and so that's really the general thinking behind why this particular special type of improper integral converges in this case, but doesn't in this case. Okay. Now, if we wanted to look at it computationally, and I'm not going to go through all the gory details on this, but at the end of the day, what you're seeing here is going to be reason why we know what we're stating up here. Okay. So if I was to actually try to evaluate this improper integral here, you see that I start off by using the definition via the type 1. And then, of course, from there, if I go ahead and move forward here and I do the antiderivative of this, you'll see that I get this and evaluate it from 1 to b. And so now I'm just rewriting this to make it easier for me to deal with. Okay. And at this point, I know that this 1 over 1 minus p is a constant. Of course, this b is going to be the thing that's changing, meaning that that's the thing that's going to infinity here. So we got to see what the different scenarios are for that based upon what the value of p would be. Okay. So in short, this is the final result that we have, but based upon whether p is negative, positive, p is less than 1, equal to 1, or greater than 1, that's going to depend upon the outcome. Okay. And so just to make the math a little bit easier, I try to replace p minus 1 with w, so that we know that this p minus 1 here will just be w whenever p is greater than 1, but when p is less than 1, we can switch it to a negative w, just to make the math easy. So in the long run, when I do all of that, if I let p be greater than 1, I see that, and knowing that b is going to be approaching infinity here, I see that whenever we evaluate all of that, I'm going to just end up getting 1 over p minus 1. Okay. And remember, since p is a constant, 1 over p minus 1 is a constant. And since it's greater than 1, this constant is not going to be something divided by 0. Okay. So it will be a real number. In the other two cases, mainly if I let p equal 1 or if I let p be less than 1, for different reasons, I'm going to end up with something that is undefined, or in terms of the limits is going to go to infinity. Okay. And so for the case where p is equal to 1, if what I'm doing here doesn't convince you, then I've actually went ahead and wrote out what it would look like if I worked it out in a more concise way. And we see here that once we do that, because of the fact that b approaches infinity and I have a natural log of absolute value of infinity, that's going to be infinity. And of course, infinity is not a real number. So saying all that to say that this is the reason why we can make this statement here that this improper integral only converges when p is greater than 1. And so instead of us going through all of this stuff from now on, what we're going to do is just use this fact and move forward with. All right, so going back to the type 2 definitions here just for a second. Again, for the type 2 definition, we know that our function, we assume that f of x can lie either above or below the x-axis. So that's what I mean by f of x being positive or negative. And we know that a lot of times we're going to end up seeing vertical asymptotes or some other type of jump discontinuity in between the values of x equals a and x equals b here, okay? All right, so to close this video out, we're going to do a few examples of being able to recognize why a particular definite integral is classified as an improper, okay? So for this first example here, we see that we're doing the definite integral of this rational function, and of course we can factor the denominator of this rational function as just x minus 2 times x minus 3, which tells us that our rational function has vertical asymptotes at x equals 2 and 3. And thus, we know that by definition, a vertical asymptote is a discontinuity. And notice that the place where we have a discontinuity is at the end value of our x value, of our limits of integration here, okay? So by definition, that makes this an improper integral, and it'll actually be a type 2A type of improper integral. And of course, type 2, those are the ones where we have the vertical asymptote showing up, or we have some other type, discontinuity at the endpoints of our limits of integration. Okay, so that's why that is a type 2A improper integral. So for part B here, notice that fact that we have this infinity here, and if we were to actually look at a graph of this, we would see that this particular function would end up having a horizontal asymptote. This is the reason why this one's an improper integral, and it's mainly because this upper limit of integration goes to infinity. It's not a real number. Okay. Now, to show that we actually have a horizontal asymptote for this function here, I go back and use a little bit of first year calculus here, and I notice that if I compare x to the fourth with 1 over e raised to the x raised to the 4, and I was to evaluate the limit of that, then, and of course using the Hopital's rule here, what I would see is that my limit would actually end up equaling 0, which means that as x approaches infinity, y approaches 0, which by definition is a horizontal asymptote on the x-axis. Okay, and so we know that type 1A type integrals, improper integrals, are the ones that sort of do that thing. We're basically trying to find the area under the curve of a function that has a horizontal asymptote, and we're trying to see, can we actually physically calculate the area under the curve, even though the upper limit goes to infinity. Okay. All right. So for part C here, we want to know, is this an improper integral? And the answer is yes. The reason why, because our lower limit here is going to negative infinity. Okay. And so this is going to be a type 1B type integral. Okay. And that's only type 1 just means that the issue here is the limits of integration itself, and not necessarily the function not being continuous. And B just means that it's the lower limit that we're talking about, not the upper limit. That's actually violating the rules of a proper integral. Okay, so this will be the end of this first video in this video series on improper integrals. The next video that I'm going to do, we're going to look at some more improper integrals, but we're going to determine whether those improper integrals are convergent or not, okay, based upon the information that we have available to us. After we do that, then of course we'll look deeper into some other theorems that we need to know to be able to figure out if an improper integral is convergent or divergent whenever we can't necessarily evaluate that by hand. All right, I'll see you in the part 2 video.